Hi, this is Kona, and I'm going to talk about hypothesis testing with a mean, or also known as a one-sample t test. So the one-sample t-test allows us to extend our hypothesis testing to cases where we don't know the population standard deviation and are also dealing with actual numbers, so numeric instead of categories. And that would be in comparison to like the z-test for the one proportion test that we've been working on the last couple of weeks. So this is kind of different from that, mostly because we don't know the population standard deviation and we are dealing with actual numbers. So no more categories, actual numbers. But because we don't know the population, we have to estimate the standard deviation, which means we have to use degrees of freedom. Degrees of freedom describes the shape of the distribution, which means it's constantly changing. And also, the larger the degrees of freedom, the closer the distribution is to being normal. So what are the steps for a one-sample t-test? The first thing, just like some of our other tests, you check for necessary assumptions. The sample observations are independent and it's a normal distribution. In general, you normally do just assume this. So unless it specifically says different, just go ahead and assume that. You then write the original claim. So is it the null or alternative? Which side is being tested? That's left, right, or middle. Calculate the appropriate test statistic. In this case, the t-test, the test statistic is the t-value. That's the observed value minus the expected over standard deviation, and that is the sample standard deviation, because we don't know the population standard deviation, over the square root of n, which is the number in our sample. Also notice the standard deviation, the sample over the square root of n is standard error. So standard error is that sample standard deviation over square root of n. We then determine a p-value associated with the test statistic using the probability calculator. So you remember probability calculator, well this time it's going to be the student's t. We enter the degrees of freedom and the t-value, click calculate, and then we pick whether it's left, right, both sides from right there. So, oh, okay, sorry about that. All right, so t-value, and then we get the p-value, and that p-value is which side. Is there enough evidence? If the p-value is less than or equal to 0.05, there is enough evidence. If the p-value is greater than 0.05, there is not enough evidence. You make a decision. Remember, if it's the null, we reject. Alternative, we support. That's from step 2A above, from your original claim. And then we've got our confidence interval. Find the critical value, once again using the probability calculator, and we do that using the student's t, degrees of freedom, and the confidence interval value in decimal goes in the middle. And we use that to find that critical value, and that's the actual t-value, where the upper is positive, the lower is negative. And then here's the actual formula you use to plug all of that information in. And also, just wanted you to note that the critical value times the standard error, so critical value times standard error is margin of error. So technically, it's observed plus or minus the margin of error, where plus or minus just means the lower limit is when you subtract, and the observed, or in the upper limit is when you add to there. So to kind of get a better feel for this, let's go ahead and do the example. So a research study measured the pulse rate of 57 college men and found a mean pulse rate of 70.4211 with a standard deviation of 9.9480. Researchers want to know if the mean pulse rate for all men is different from the standard of 72. And then along with that, find the lower limit of a 95% confidence interval. So the first part is, remember we go up here, check any necessary assumptions. We're just going to go ahead and assume both of those are true. So, okay. The next part, write the original claim. Is it null or alternative? So if you look at this, the original claim is the mean pulse rate for college men is different from the standard of 72. So the mean pulse rate for all college men is different from the standard of 72. And so remember, different would mean not equal. So that's where you're getting that it's the alternative right there, right? Because different is not equal, alternative. Also, because we're just talking about it being different, we're not talking about it being less than or more than. It's going to be both sides or both tails. So that's the second part. 3 is then calculating our t statistic, our test statistic here. So we take our observed, which is right here, and that is the 70.4211, minus our expected, and that is the 72, the standard of 72. So that one minus 72 over our, so if you look right here, our standard error, which is the standard deviation of our sample, over the square root of n, which was 57. So if we go ahead and do that out on our calculator, so here we go, turn this on. So I'm going to do parenthesis 70.4211 minus 72, close the parentheses, divide it by, then a parenthesis 9.9480 divided by the square root of 57. Close that parenthesis, close the second parenthesis, hit enter, and you get the negative 1.98274386. So there's our t. The fourth thing we do is then determine a p-value associated with the test statistic. So for this one, we need our degrees of freedom, which remember degrees of freedom is n minus 1, is 56. So we're going to come over here, and our degrees of freedom is 56. Then we also enter in our t value. Where's t? Okay, so over here, then we enter t, negative 1. Yeah, okay, you can tell I've been doing it. Okay, and then we click calculate. So we have the left side, right side, both sides, and what we need to figure out is which p-value we're using. So to determine which p-value we're using, we go back to that it was an alternative with both sides. And we determined that because of it's different. So because it's different, that was alternative, that's a both sides. So when we look at left side, right side, both sides, which are our possible answer options right here, we're going to go with the both sides because of what our hypothesis was. So in this case, our p is the 0.2358 5857. Okay, so put it over here. So then we compare our p to 0.05, and 0.235857 is greater than or equal to 0.05, which makes this an is not. So when we put that back in to come up with our conclusion, there is not, and that's because of the p-value, enough evidence to support. We're supporting because this was an alternative, so we always support the alternative. So there's not enough evidence to support the claim that the mean pulse rate for all college men is different from the standard of 72. So what does that actually mean? So there's not enough evidence to support the claim that the pulse rate is different from 72. So what that means is that basically we're saying it doesn't appear to be different. You can never prove anything, so please do not ever use the word prove. So we can't prove it, but it appears from our data that the mean pulse rate isn't different. So then we want to define, remember, that lower limit of a 95% confidence interval. Well, to do that, you need that critical value. And to find the critical value, so over here, what you do is you put in the 56 for your degrees of freedom. Then over here where it says middle, you do the 0.95. And where that 0.95 is coming from is right here, find the lower limit of a 95% confidence interval. Okay, so 0.95, and click calculate, and you get two t values. Well, how you know which t value to use is basically whether you're doing upper or lower. So this one asked for the lower. That's why we did a negative 2.003241. If it had asked for an upper, then we would have used the positive 2.003241. So positive, or the upper is the positive value, lower is the negative value. So, but we do look at these t values right here. So we did our 70.4211, and so that value right there came from here. So that's our observed minus our critical value, which we just figured, and that was from using the probability table, times our standard error, and that standard error was the sample standard deviation divided by the square root of n, which was our 57. And I'm not going to do this one on the calculator, but if you do it on the calculator, you get your 67.78153,994, and that's your lower limit of your 95% confidence interval. So there you go. There's an example, and I hope this all helped and made sense.